Many of the distributions you use in data science are not discrete binomial and instead are continuous, where the value of the given observation isn't a category like heads or tails, but can be represented as a real number. It's common to then graph these distributions when talking about them, where the x-axis is the value of the observation and the y-axis represents the probability that a given observation will occur. If all numbers are equally likely to be drawn when you sample from it, this should be graphed as a flat horizontal line. And this flat line is actually called the uniform distribution. There are a few other distributions that get a lot more interesting. Let's take the normal distribution, which is also called the Gaussian distribution or sometimes a bell curve. This distribution looks like a hump, where the number which has the highest probability of being drawn is 0, and then there are two decreasing curves on either side of the x-axis. One of the properties of this distribution is that the mean is 0, and that the two curves on either side are symmetric. I want to introduce here the term expected value. I think that most of us are familiar with the mean as the sum of all of the values divided by the total number of values. Calculating a mean value is a computational process, and it takes place by looking at samples from a distribution. For instance, rolling a die 3 times might give you the numbers 1, 2, and 6. The mean value is then 4.5. The expected value is the probability from the underlying distribution. That is, what would be the mean of a die roll if we did an infinite number of rolls? The result is 3.5, since each face of the die is equally likely to appear. Thus, the expected value is 3.5, while the mean value depends upon the samples that we've taken and converges to the expected value given a sufficiently large sample set. We'll talk more about expected values in Course 3. A second property is that the variance of the distribution can be described in a certain way. The variance is a measure of how broadly the values of samples are spread out from the mean. Let's get a little bit more formal about 5 different characteristics of distributions. First, we can talk about the distribution's central tendency, and the measures we would use for this are mode, median, or mean. This characteristic is really about where the bulk of the probability is in the distribution. We can also talk about the variability in the distribution. There are a couple of ways we can speak of this. The standard deviation is one, the interquartile range is another. The standard deviation is simply a measure of how different each item in our sample is from the mean. Here's the formula for standard deviation. It might look a little more intimidating than it actually is. Let's just walk through how we would write this up. Let's draw 1,000 samples from a normal distribution with an expected value of 0.75 and a standard deviation of 1. Then we calculate the actual mean using NumPy's mean feature. The part inside the summation says xi minus x bar. Xi is the current item in the list, and x bar is the mean. So we calculate the difference, then we square the result, then we sum all of these. This might be a reasonable place to use a map and apply a lambda to calculate the differences between the mean and the measured value, then to convert this back to a list so NumPy can use it. Now we just have to square each value, sum them together, and take the square root. So that's the size of our standard deviation. It covers roughly 68% of the area around the mean, split evenly on either side of the mean. Now, we don't normally have to do all of this work ourselves, but I wanted to show you how you can sample from a distribution, create a concise programmatic description of a formula, and apply it to your data. But for standard deviation, which is just one particular measure of variability, NumPy has a built-in function that you can apply called std. There are a couple of more measures of distributions that are interesting to talk about. One of these is the shape of the tails of the distribution, and this is called the kurtosis. We can measure the kurtosis using the statistics functions in the SciPy package. A negative value means the curve is slightly more flat than a normal distribution, and a positive value means the curve is slightly more peaky than a normal distribution. Remember that we aren't measuring the kurtosis of the distribution per se, but of the 1,000 values which we sampled out of the distribution. This is a subtle but important distinction. We can also move out of the normal distributions and push the peak of the curve one way or the other, and this is called the skew. If we test our current sample data, we see that there isn't much of a skew. Let's switch distributions and take a look at a distribution called the chi-squared distribution, which is also quite commonly used in statistics. The chi-squared distribution has only one parameter called the degrees of freedom. The degrees of freedom is closely related to the number of samples that you take from a normal population and is important for significance testing. But what I would like you to observe is that as the degrees of freedom increases, the shape of the chi-squared distribution changes. In particular, the skew to the left begins to move towards the center, and we can observe this through simulation. First, we'll sample 1,000 values from a chi-squared distribution with degrees of freedom 2. Now we can see that the skew is quite large. Now if we resample changing degrees of freedom to 5, we see that the skew has decreased significantly. And we can actually plot this right in the Jupyter Notebook. I'm not going to talk much about the library we're using here for plotting because that's the topic of the next course. But you can see a histogram of our plot with the 2 degrees of freedom is skewed much further to the left, while our plot with the 5 degrees of freedom is not as highly skewed. I would encourage you, as always, to play with this notebook and change the parameters and see how the degrees of freedom changes the skew of the distribution. The last aspect of distributions that I want to talk about is the modality. So far, all of the distributions I've shown have a single high point, a peak. But what if we have multiple peaks? This distribution has 2 high points, so we call it bimodal. These are really interesting distributions and happen regularly in data mining. We're going to talk a bit more about them in course 3, but a useful insight is that we can actually model these using 2 normal distributions with different parameters. These are called Gaussian mixture models and are particularly useful when clustering data. Well, this has been a long lecture, but I think it can be tough to chop up a discussion of distributions and still get the main points across. Remember that a distribution is just a shape that describes the probability of a value being pulled when we sample a population. And NumPy and SciPy each have a number of different distributions built in for us to be able to sample from. The last point I want to leave you with here is a reference if you find this way of exploring statistics interesting. Alan Downey wrote a nice book called Think Stats by the publisher O'Reilly. I think he does a really nice job of teaching how to think about statistics from a programming perspective, one where you write the functions behind the statistical methods. It's not really a reference book, but it's an interesting way to approach learning the fundamentals of statistics. Alan even has a free copy of this book available on his website in PDF format, and of course, all of the code is done in Python.